In this session, we are discussing some of the numericals from the chapter standard 12th. Question number 1. If 5.85 gram of NaCl is dissolved in water, the solution is made to 0.5 liter. The molarity of the solution is. Generally, the molarity of the solution is calculated by weight of the substance divided by the molecular weight of that solute multiplied by volume of solution in liter. So now here they have given us 5.85 grams of the substance is being dissolved in around 0.5 liter of water, and molecular weight is 58.5. So if we'll calculate this, the answer comes out to be 0.2 molar. So therefore option A. Question number 3. How many grams of dibasic acid should be present in 100 ml of its aqueous solution to give decinormal solution? Usually when I'm talking about normality, we take weight of the solutes divided by its equivalent weight multiplied by volume that has to be present in liter. Now they have given us decinormal solution. So normality has to be 0.1, that's equals to the weight of substance we need to calculate. Now this is dibasic acid. So the basicity of this is 2. Equivalent weight is a molecular weight divided by the basicity. So molecular weight is 200 divided by 2, that is 100, multiplied by the volume which is given here 100 ml, that's 0.1 liter. Therefore the W is 1 gram. Option A. Question number 13. A 0.1 molar aqueous solution of weak acid is 30% ionized if HKF of the water is 1.86 degrees Celsius per molar. The freezing point of the solution we need to calculate. Now in this case, first of all they have given us alpha, that is 30%, that's equals to 0.3. Now if I have to calculate, since it is the dissociation reaction, we need to calculate the Van 't Hoff factor, that is equals to 1 plus alpha, that is 1 plus 0.3, that's equals to 1.3. Now delta TF, we have a formula that's equals to I into KF into molality. So I is 1.3, the KF is given is 1.86 multiplied by the molality of the solution is given is 0.1. So if we calculate this, we'll get the answer. It's 0.241. This is the difference in the boiling point, the freezing point. So we need to calculate the freezing point of the solution. It should be minus 0.24 degrees Celsius. Therefore option B. Question number 16. The solution containing 10 grams per dm cube of urea is isotonic with 5% solution of the non-volatile solute. The molecular mass of the non-volatile solute we need to calculate. Now in this equation we know it's pi 1 is equals to pi 2, that's isotonic solution. So concentrations are also equal. Now first solution is 10 grams, that's dissolved in 1 liter. So molecular weight is 60, dissolved in 1 liter of solution. That's equal, so this is 5% solution. So it is kind of thing like if I'm talking about 5%, it's 5 gram in 100 ml. So 50 grams in 1000 ml. So 50 multiplied by molecular weight in 1 liter. Therefore if we calculate this, the M comes out to be 300 gram per mole. Therefore option A. Question number 24. Ethylene glycol is used as a anti-freezing in the cold climate. The mass of the ethylene glycol which should be added to the 4 grams of water to prevent it from freezing at minus 6 degrees Celsius will be. First of all, they have given us delta TF. This is minus 6 degrees Celsius freezing point. So delta TF will be 6 degrees Celsius. The KF is given over here. It's 1.86. Molality, weight of the substance we have to calculate. Molecular weight is given to us. So we have a formula delta TF is equals to KF into molality. So delta TF, that is 6, that's equals to KF is 1.86. Molality is a weight of the substance divided by its molecular weight. Molecular weight is given 62 multiplied by the weight of the solvent in kg, that is 4. So when we will calculate this, the W comes out to be 804.32 grams. Therefore option A. Question number 25. The freezing point constant for the water, that is KF, is given to us. If 342 grams of cane sugar are dissolved in 1000 gram of water, what will be its freezing point? So delta TF is equals to KF into molality. So delta TF, we are going to find out. KF is 1.86. Molality is the weight of the solute, which is 342 divided by the 1000 grams of the water, that is converted into kg, so 1 kg. And molecular weight of the cane sugar is also 342. So answer comes out to be 1.86 only. So TF will be equals to minus 1.86 degrees Celsius. Therefore option A. Question number 3. An element having atomic mass of 100 grams per mole, having BCC structure, has unit cell edge length, that is 400 picometer. What is the density of this element? We have a formula density, that is Z into M, Na into A cube. Now this is BCC structure, so number of atoms per unit cell is equals to 2. Molar mass given is 100. Na, Avogadro's number, is 6.02 into 10 raised to 23. The edge length A is given to us, that is 400 picometer. That's equals to 4 into 10 raised to minus 8 centimeter. So A cube will be 4 into 10 raised to minus 8 cube. So when you will calculate this particular thing, you will get answer of 5.188 gram per centimeter cube. Therefore answer B. Question number 10. In FCC centered cubic cell, an atom at the face contributes to the unit cell. Each atom which is present at the face, it is contributing the half portion to the unit cell. Therefore option D. Question number 15. The copper crystallizes in FCC with the unit cell length, that is A is given to us. This is 361 picometer. We need to calculate the radius. For the FCC crystal, we have 4R is equals to root 2A. Therefore, A, that is R, is equals to root 2A divided by 4. So this is root 2 multiplied by 361 divided by 4. So this answer comes out to be around 127 picometer. Hence option B. Next question, number 23. The percentage of the free space in the cubic closed pack structure and the body centered pack structures are respectively. When we talk about CCP, the closed packing is around 74%, and in case of body center, it is 68%. So if we'll subtract these numbers from 100, we'll get the free space. So this having free space of 26% and this is having free space of 32%. Therefore, option C. Question number 28. The coordination number of a metal crystallizing in a hexagonal closed pack structure. When I'm talking about HCP, in which every atom is surrounded by 6 atoms in the hexagonal fashion in the same plane, 3 atoms above the plane and 3 atoms below the plane. So every atom, if we'll count, it's surrounded by 6 atoms in its own plane, 3 atoms above, 3 atoms below. That makes total coordination number of 12. Question number 7. 1 mole of an ideal gas is allowed to expand reversibly and adiabatically from temperature 27 degrees Celsius. If the work done during the process is 3 kilojoule, the final temperature of the gas we need to calculate. They have given us the CV value of 20 joule per Kelvin. So we'll convert first of all this value of the heat which is given, the work done which is given, that's equals to 3 kilojoules. So that is 3000 joule. Now we'll use the formula. The work done is equals to minus NCV into T2 minus T1. Now this work done is 3000, that's equals to, the number of moles is given is 1 multiplied by 20 specific heat T2 that we need to calculate minus T1 given is 300. So if you calculate this particular answer, you will get T2 is equals to 150 Kelvin. Therefore option B. Question number 11. If the enthalpy change for the transition of a liquid water to steam is 30 kilojoule per mole at 27 degrees Celsius, the entropy change we need to calculate. Now we have a formula, delta S of vaporization is equals to delta H upon T. The delta H is given to us, that is 30 kilojoule per mole divided by the temperature is 300. So when you calculate this comes out to be around 0.3, that is nothing, sorry, 0.1, that is nothing but 100. This is in kilojoules, so 100 joule per mole per Kelvin. Therefore option A. Question number 12. Standard entropy of X2, Y2 and XY3 are 60, 40 and 50 joule per Kelvin per mole respectively for the reaction. Delta H is given. Then we need to calculate the entropy of that particular reaction. The corresponding entropies are given to us. So first of all, delta H of this reaction will be equals to, now this is in the case of the entropies, this is related to X2, entropy given is 60, Y2 given is 40, and in case of the XY3 it is given 50. Now delta, first of all we'll calculate delta S. Delta S is equals to entropy of the product is XY3, that is 50 minus the entropy of the reactant. Reactant is X2 but it is half of the X2. So we'll take 60 divided by 2 plus this is 3 by 2 of Y2. So 3 by 2 multiplied by 40. So when we'll calculate this, the answer comes out to be minus 40 joule. Delta H of the reaction is given already, that is minus 30 kilojoule, that's nothing but minus 3000 joule. Now if we'll calculate the temperature is equals to delta H upon delta S. So this is minus kilojoule, that is 30,000. So 30,000 divided by minus 40, that comes out to be 750 Kelvin. Option B. Question number 13. The heat evolved in the combustion of a benzene is given by the reaction. This is involving 1 mole of benzene over here. Which of the following quantities of the heat energy will be evolved if the 39 grams of benzene are burned? In case of benzene, the formula is C6H6. So there are 6 carbon. So if we calculate the molecular weight of this, it's 78. So for 78 grams, the energy is 3264. So we need to calculate for 39 grams. 39 is exactly half of this. Therefore, the answer will be half of the 3264, that is 1632.3 kilojoule. Option B. Question number 26. The following reaction occurring in the automobile. In this case, the sign of delta H, delta S and delta G we need to calculate. Now in case of delta H will be negative as the reaction is the combustion reaction and all combustion reactions are exothermic in nature. In case of delta S, we'll calculate the number of moles. If you look at the product side, it is 18 plus 16. So this is 16 plus 18 minus the reactant side is 25 plus 2. So answer is coming plus 7. So delta S will be plus 7 positive. And in case of delta G, the reaction will be spontaneous. Therefore delta G will be negative. So answer is negative, positive and negative. Therefore option B. Question number 30. The bond dissociation enthalpies of H2, Cl2 and HCl are given. Enthalpy of formation of HCl we need to find. Here the bond enthalpies are given. Therefore, delta H of the reaction will be the heat of bond enthalpies of the reactant minus product. So we have a reactant over here. In case of HCl formation, we need half of H2 will react with half of Cl2 to give HCl. So half of enthalpy of hydrogen, that is 434, plus half of enthalpy of chlorine, that is 242, minus the enthalpy of the HCl, that is 431. So if we'll calculate this, the answer is minus 93 kilojoule per mole. Therefore option A. Question number 3. The rate of the reaction is doubled for every 10-degree rise in temperature. What is the increase in the rate of reaction as a result of temperature rise from 10 raised to 0 to 10 raised to, that is 10 degrees Celsius to 100 degrees Celsius. Now when I'm talking about this reaction, for every 10-degree rise, the reaction becomes double. So from 10 to 100, it is almost 2 raised to 9 times. So that comes out to be 512. So option B. Question number 4. For the reaction A plus B giving product, it was found that the rate of reaction increases 4 times if the reaction of concentration of A is doubled, but the rate of reaction remains unaffected if the concentration of B is doubled. So now in case of the rate of reaction, it is unaffected with the concentration of B. So we will not involve the concentration of B in the rate law. So it will be K into A raised to X. We need to find the value of X. The new rate, it has been found, it is 4 times of the original when the concentration of A becomes double. So if we will take the ratio, this is 1 by 4 is equals to 1 by 2 raised to X. Therefore, X is equals to 2. Therefore, the rate law is rate is equals to K into A raised to 2. Option B. Question number 10. For the reaction H2 plus Br2 giving twice of HBr, the experimental data suggests the rate K into H2 concentration, Br2 concentration raised to half. The molecularity and the order of reaction. Here, one molecule of H2 will react with bromine. Therefore, molecularity of the reaction is 2, while the order of reaction with respect to hydrogen it is 1 and with respect to bromine it is 1 by 2. So total is 3 by 2. So answer is 2 and 3 by 2. Hence option A. Question number 11. The rate constant for the first order reaction is 3 into 10 raised to minus 6 per second. If initial concentration is 0.1, then the initial rate of reaction we need to find. So rate of reaction is equals to K into concentration. K is given to us, that is 3 into 10 raised to minus 6 multiplied by the concentration given 0.1. The answer comes out to be 3 into 10 raised to minus 7. Hence option D. Question number 15. 75% of the first order reaction was completed in 32 minutes. When was the 50% of reaction is completed? So the first T is equals to 2.303 upon K log to the base 10. Initial concentration is 100 and since it is 75% completed, the remaining is 25. So here it is 32, that's equals to 2.303 upon, now since they have asked us for the 50%, 50% is nothing but the half-life. So half-life T half is equals to 0.693 upon K, that is in short K is equals to 0.693 upon T half. So I am just putting instead of K 0.693 upon T half log of 4. Therefore T half will be equals to 32 multiplied by 0.693 divided by 2.303 into log of 4 is 0.6020. So that comes out to be around 16 minutes. Hence option A. Question number 17. From the decomposition of the compound AB at 600 Kelvin, the following data were obtained. The concentrations of AB given and the rate of decompositions are given. So let us write the rate equation according to the case 1. Case 1 says the rate of equation is 2.75 into 10 raised to minus 8, that's equals to K into concentration 0.20. Let us assume it raised to N. Then next is 11 into 10 raised to minus 8, that's equals to K, that is your case 2, into concentration of 0.40 raised to N. If I'll divide the equation 2 by 1, then I will get the answer on left hand side. If we'll divide, this answer comes out to be around 4, that's equals to K into 2 raised to N. Therefore N is equals to 2. So the order of reaction is 2, option C. Question number 18. The rate equation of the reaction A is giving B is K into R is equals to K into A concentration raised to 0. The initial concentration of the reactant is mole per dm cube. The half-life period we need to calculate. This is zero order reaction since it is written A raised to 0. And for zero order reaction, the T half is directly proportional to the initial concentration. So T half is equals to A upon 2K, option D. Question number 6. 4 grams of copper was dissolved in concentrated nitric acid. The copper nitrate solution was on strong heating gave 5 grams of its oxide. Now this 5 grams of oxide is containing 4 grams of copper and 1 gram of the oxygen. So if we'll calculate copper and oxygen, weight we got 4 grams and this is 1 gram. This is 4 divided by atomic weight of copper is 63.5. So this comes out to be 0.0625 and this is 1 divided by 16, that is oxygen 1 divided by 16, that comes out to be 0.0625. So the ratio is 1:1. So the formula of the compound is CuO. Now in this compound if you can see the copper is present in +2 oxidation state. So equivalent weight of the compound is 63.5 divided by 2. So that is 31.75. So it is approximately 32. Question number 7. The charge required to liberate 11.5 gram of sodium. Now in case of sodium, sodium plus gains 1 electron to become Na. So 1 mole of sodium, that is 23 grams of sodium will be obtained from 1 Faraday of electricity. 11.5 is exactly half of the 23. So it will be obtained from 0.5 Faraday of electricity. Question number 15. The standard reduction potentials at 298 Kelvin are given. For zinc it is minus 0.762. For chromium minus 0.740. Hydrogen 0 and iron 0.770. Which is the strong reducing agent?